We are going to start now the second part of our chapter 5 Euclid geometry of class 9 mathematics. So in this lecture we will discuss about the problems based upon what we have studied in lecture 1. So the first theorem we have to prove over here, it is prove that two distinct lines cannot have more than one point in common. So how we are going to prove is, first we are talking about what is given to us is two distinct lines L and M are given to us, and what we have to prove is we have to prove that L M M cannot have more than 2 points in common. So what we are saying is, first there are two cases over here. First case, if L M and M we are considering they are parallel, then clearly there is no point common or no common point between these two lines. So our theorem is satisfied, but our theorem is saying that cannot have more than one point. Cannot have more than one point means it will have less than or equal to 1 point. It means either it has 0 point in common or 1 point in common. So we are saying when L is parallel to M, there is 0 point common, that is no point is common between these two. Now in the second case, we are saying suppose L is not parallel to M. It is written like this symbol we are talking over here. It is like this, that L is not parallel to M. Then suppose we are saying it has more than 1 point in common. We have to prove that it has either 0 point or 1 point in common. What we have considered over here, it has more than 1 point in common. This is, we have this thing we have considered. And suppose we are saying it has more than 1 point means it has at least 2 points in common, and let those points be P and Q. Now what we can do is, we know that if 2 points P and Q are given to us, we can always draw a unique line passing through P and Q. It means what we are saying, L is not parallel to M. Now we are considering that there are 2 points which are common to this. Those 2 points are P and Q, and we are saying that the axiom we have, it was that from two distinct points we can always draw a unique line. There is only one line. It means both these lines will be same. L and M will be same. That is, L is equal to M. But it is given to us that these two lines are distinct lines. So what we are saying, we are saying it is given to us that these two lines are distinct lines. So we are saying we reach at a contradiction. We reach at a contradiction. So our supposition, what we have supposed, that it has more than 1 point in common, this supposition is wrong. This supposition is wrong. It means it cannot have more than 1 point in common. So we have proved this theorem that two distinct lines cannot have more than 1 point in common. Next we have is the parallel line axiom. It is, if P is a point outside a given line L, then one and only one line can be drawn to pass through P and parallel to L. So it is, a line is given to us. This is the line L that is given to us. A point P is given to us. this is the point P, and we are saying that if we want to find a line which is parallel to this line L and it is passing through the point P, then there is only a unique line. This one and only one line means we are saying it is a unique line M. So what we get from this is that two intersecting lines cannot be both parallel to a given line. So how we are going to prove this? So suppose we are saying that a line is given to us and two intersecting lines are given to us. If these two lines, these are intersecting lines, it means they will have a point P over here which is common to both these lines. This is by the definition of the intersecting lines. We know they intersect at a point. So that point, we are saying that point is P. Now what we are saying is, from our parallel line axiom, what we know is, if this line L is given to us and a point P is given to us, and if we draw a line from passing through P and parallel to L, if we draw a line passing through P and parallel to L, then this line M is unique. This thing is coming from our parallel line axiom. So it means there can only be one line which is passing through P and which is parallel to L. So if two intersecting lines are there, it means only one of these two lines, if two intersecting lines are there which are passing through the point P and parallel to a given line, it means only one of these lines can be parallel to the given line. Both of these lines cannot be parallel to the given line. Now we will use this thing in our next theorem. So we have to prove that, the next theorem we have, prove that the lines which are parallel to a given line are parallel. So to prove this, what we are saying is, what is given to us is, three lines are given to us, L, M and N, and the condition that is given to us is that L is parallel to N and M is parallel to N. We are saying a fixed line N is given. This is a fixed line. Two more lines are given. One is the line M and one is the line, say, L, and it is given that L is parallel to N and it is given that M is parallel to N. We have to prove that, what we have to prove is that L is parallel to M. So we prove this statement by using the method of contradictions. So method of contradiction means that we suppose something and we start with that supposition and we reach at some point which will show us that whatever we have reached, it is mathematically incorrect. So when it is mathematically incorrect, we will say that whatever we have supposed, it is wrong. So in this case, what we are going to suppose is, we are saying, if possible, let M is not parallel to M. We have to prove that L is parallel to M, and we are supposing that if possible L is not parallel to M. So basically we are saying, suppose L is not parallel to M. Now if L is not parallel to M, then what will be there? We are saying there is a unique point P which is the point of intersection of L and M, because these are intersecting line now, and this point P will lie outside N. So what we have is that, what we are saying over here, it is, we are having two intersecting lines L and M, their point of intersection is P, and there is another line, we are saying it is N over here. Now we are saying this point P is lying outside this line N. So what we have now is, we are saying that we have a line N, we have a point P, and two lines are passing through the point P. Now what is given to us is that these two lines, we are talking about L and M, what is given to us in the problem, that L is parallel to N. This thing is given to us, that L is parallel to N, and it is given to us that M is parallel to N. And from our previous result we know that if we have two lines parallel to a given line, then we have two intersecting lines cannot be both parallel to a given line. So from this previous result we are saying we are reaching a contradiction, because what we have obtained from here is that we are saying L and M, they are intersecting lines, but they are parallel to the same line N. So this is the point from which we are getting the contradiction. So contradiction is because we have assumed something wrong. Our assumption is wrong. So what we have assumed, that L is not parallel to M, this assumption is wrong. So what we say, that L is parallel to M. The next thing we have to prove is that if lines AB, AC, AD and AE are parallel to line L, then we have to prove that A, B, C, D and E are collinear. So again, what is given to us is AB, AC, AD and E are lines all parallel to a line L, and what we have to prove is that A, B, C, D and E are collinear. So first thing we are saying that a line L is given to us. Now as AB, AC, AD and AE are lines parallel to L, so we are saying that A is some point outside L. Now by parallel line axiom, what we are saying, we can draw a unique line. This line is unique, one and only one line we can draw, which is parallel. Suppose I am saying this line is M, so M is parallel to L and M passes through A, and this line M, it is unique. Unique means it is only one and only one line is there. So if this line M is unique and we are given that A, B, A, C, A, D and AE are parallel lines to L, and all of these lines, these are passing from the point A, so what we reach from this is that A, B, C, D, E we are talking about, these are just the points over here, B, C, some D, some point E is there. So all these, they lie on this line. These all points lie on M. And if these all points, they lie on M, this is the definition of the collinear points. So we have proved that A, B, C, D and E are collinear. So what we have done, the line L is given to us. We are saying that we have a unique line M which can pass through A and which is parallel to L. We are saying all these points A, B, C, D, E, they lie on this line M. Now as they lie on this line M, so we are saying that all these points, these are collinear points. Now the next we have, if A, B and C are 3 points on a line and B lies between A and C. So A and C are points there and B lies between A and C. We have to prove that AB plus BC is equal to AC. So what we are saying, how we are proving this, we say we draw the figure over here. This figure we have shown over here. So what we are saying is that AC coincides with AB plus BC, and the Euclid's fourth axiom, it was saying that the things that coincide with one another are equal to one another. So we are saying that AB plus BC is equal to AC. So we have used this figure to prove that AB plus BC is equal to AC. The next theorem we have, if a point C lies between points A and B such that AC is equal to BC, then we have to prove that AC is equal to 1 by 2 times AB. So again we draw the figure over here. So we are saying that we consider 3 points on a line such that AC is equal to BC. We have drawn a line and we have considered the point ABC in this form. Then from the Euclid's axiom 2 we are talking about, what we have is that if equals be added to equals, then the wholes are equals. So what we are saying is that if I am talking about AC is equal to CB, I am talking AC plus I am adding AC to it and AC plus CB. So basically we are saying that we are having AC is equal to AC and these two terms are equal. We have added these values over here, so we get plus AC plus CB. Now what AC plus AC will be equal to? This is 2 times AC. Now AC plus CB, that is equal to AB. This thing we have proved in the previous theorem. So what we get from this is that AC is equal to 1 by 2 times AB, and this is what we have to prove in this theorem. Now next is, the figure is given to us and it is given that AC, this AC is equal to BD, and we have to prove that this AB is equal to CD. So what we are going to use over here is the Euclid's second axiom, which says that if equals be subtracted from equals, then the remainders are equals. So how we start proving this is, we are saying AC is equal to BD. This is given to us. This thing is given to us, and we subtract BC from both sides, that is BD minus BC. We are subtracting this BC from the both sides. So the answer we are left with is AB is equal to CD. From this we have subtracted this BC part, from this we have subtracted this BC part. So what we are left over here, it is AB, and what we are left over here, it is CD, and this is what we have to prove. Similarly, it is x minus 5 is equal to 15. You have to solve this equation. So this is not basically a geometrical problem, this is an algebraic problem. So similar kind of approach we can use over here. We are saying we are using the Euclid's second axiom, which says that if equals are added to equals, then the wholes are equals. So I hope it is more clear to you what is the meaning of this term. So we have started over here, x minus 5 is equal to 15. Next, equals are added to equal. These two terms, these are equal. So we are saying equals we are adding means we are adding 5 on both the sides. So the answer you will get is equal to x is equal to 20. So equals are added to equal mean these values are equal to each other. What we have done, we have added equals to them on both the sides over here. So the answer you will get it is x is equal to 20. Now the next thing we have is prove that an equilateral triangle can be constructed on any given line segment. We have to prove this thing, that is a line segment of given length is given to us. We are saying suppose AB is a line segment that is given to us and it has some fixed length. Then with A as center and AB as radius, we draw a circle over here. We are saying with A as the center and AB as radius, we draw a circle over here. So suppose this is the circle we are drawing over here. This is the circle with A as the center and AB as radius. Next, we have to draw another circle with B as center and AB as radius. This is the circle with center B, radius AB. Now the points where these circles they intersect, suppose we are saying this is the point, this point, it is the point C, and in the next step we join AC and we join BC. So we claim that this triangle ABC is an equilateral triangle. Now we have to prove this thing. Now as we have drawn the circle over here, this is the circle. So what we are saying that the length AB that is equal to AC and the length AB that is equal to BC. Why? Because suppose I am talking about this is a circle over here. This is the center of the circle A and this is the point B. There is another point C on this circle. So if I will join these 2 points, this is the radius of the circle, this is the radius of the circle. So it means we are saying AB is equal to AC. Similarly, when we are talking about this is our line AB and we have drawn the circle like this length we are saying it is R. The point C is over here. So if I join these 2 points, this is also R. So from these 2 results we are getting that AB is equal to AC and AB is equal to BC. Now from the Euclid's first axiom we have the things which are equal to the same thing are equal to one another. So AC is equal to AB, BC is equal to AB. So we get AC is equal to BC. So combining these 3 results, what we get is that AB is equal to AC is equal to BC. So all the 3 sides of the triangle are equal, and this is what the definition of equilateral triangle is, that all the 3 sides should be equal. Now in the next question we have a triangle ABC is given, in which it is given that this side AB that is equal to BC, and second thing that is given is that BX is equal to BY. Now we have to prove that this AX is equal to CY. So what we see from this is, if we look at this figure, so basically we are talking about that AC is equal to BC is given. If we subtract, second thing that is given to us is that BX is equal to BY. So if I subtract these values from this, it is minus BX minus BY. So what we are saying? We are saying that equals are subtracted from equals. And when equals are subtracted from equal, the remainders are equal. So this equality sign is there. So what we are left now? AC minus BX, that is equal to, sorry, it is not AC, it is A. B minus AB is equal to BC is given to us. So when we subtract these values, we get it is AX is equal to CY. What we are saying, this line is AB, this point is X. If we subtract AB, if we subtract BX from AB, what we are left with is AX. Similarly, we have the second line over here. It is like CB. This is the point Y, and if we subtract this BY from this, we are getting it as CY. So this is what we have to prove in this case, that AX is equal to CY. Now in the next question, it is given that this figure is given, and we are given that this angle A1, that is equal to angle 3, and angle 2 is equal to angle 4, and we have to prove that this angle A means this total angle, is equal to angle C. So we are saying angle 1 is equal to angle 3, angle 2 is equal to angle 4. So both these are equal. Now if I add these values means I am adding, say, angle 2 to this and angle 4 to this. So what we are using over here, it is when equals are added to equals, the wholes are equals, and the total angle, this total angle, it is angle A, and this total angle, it is angle C. So we are saying we have obtained this answer. Similarly, in the next question, it is angle 1 is equal to angle 3. This angle 1 is equal to angle 3, and angle 2 is equal to angle 4. Further, it is given that angle 3 is equal to angle 4. So what we see from this is that angle 1 is equal to angle 3 and angle 3 is equal to angle 4. This is given to us. So by Euclid's first axiom, what we get is that angle 1 is equal to angle 4. By Euclid's first axiom, we will get angle 1 is equal to angle 4. Now what is given to us is angle 2 is equal to angle 4. This is given to us, that angle 2 is equal to angle 4. Now combining these two values and using Euclid's first axiom, what we get, it is angle 1 is equal to angle 2, and this is what we have to prove. So what we have used over here is that things which are equal to the same things, they are equal to one another. So we are saying 1 is equal to 3, 3 is equal to 4. So it means 1 is equal to 4. Second thing that is given to us is 2 is equal to 4. So both 1 and 2, they are equal to 4. So we are saying 1 and 2, they are also equal. So from this we get that 1 and 2, they are also equal. Now in the next question, these are true and false type questions. So first is a simple closed figure made up of 3 or more line segments is called a polygon. So this is just the definition of polygon, that is any closed figure which has more than 3 or more than 3 sides. So we are talking about triangle, rectangle, square, if pentagon is there, hexagon is there. So these all, they have more than 3 sides. So these all are polygons. Second we have is part of a line with 2 endpoints is called a line segment. So this is also true. We have studied this definition earlier also, that it has 2 endpoints and it is line segments. Next is in geometry, we take a point, a line and a plane as undefined terms. So there is no fixed definition for a point. Point, we are saying it is just the location of some, it is just the position of some location. It is just the point. And there are no fixed definitions for these terms. And then the next is the Euclid's fourth axiom says that everything equals itself. This is also true. This is Euclid's fourth axiom. Then the Euclidean geometry is valid only for figures in the plane. This is also true, because if the surfaces are curved, then these axioms does not hold. As we have seen earlier also, we suppose it is a curved surface we are talking about, and we are saying that these 2 points A and B are there, then another point, say we are saying B and suppose this point C is there. So if we are talking about the straight line, you cannot draw the straight line over here. The definition that we have seen earlier, that it is the closest distance between the closest distance between the 2 points, it fails over here. And other things also fail when the surfaces we have, they are not the plane surfaces. So what we are saying, that Euclidean geometry is only valid for the plane surfaces. Then the last is, a figure formed by two rays with a common initial point is called an angle. So this is just the definition of angle we have, and this is also